what does it mean when someone asks you to find the nth roots of unity? Well, what they mean when they say this is they want you to find n numbers such that when they're raised to the nth power, it equals 1, right? And a good way to formulate this, we'll put it quantitatively, is just this polynomial equation right here. You want n numbers, right? Because, well, x is just going to be what your number is. And when you raise it to the nth power, it's equal to 1. And keep in mind that since this is a polynomial equation of nth degree, there are going to be n solutions, right? So if, say, this were to be x to the 5th power is equal to 1, you're looking for 5 numbers, which when raised to the 5th power, all equal to 1. Yeah, pretty simple concept. So let's go over all of them. Not all of them. That's not possible. There's infinitely many, technically. But for now, we're going to be going from n is equal to 1 to n is equal to 8, right? And of course, there are a few exceptions. Well, just one exception. We're not going to do n is equal to 7. And I'll explain why towards the end. But for now, let's get started. So the first one is pretty simple, right? X to the nth power, in this case, the first one, we're just going to use 1, is equal to 1, right? And for this, notice how the degree is 1, so you're only going to have one solution. And this is really simple, because the solution is right there. You just get x is equal to 1. Since there's only one number when raised to the first power, that still returns 1. Out of all the algebraic numbers, at least. It's just x is equal to 1, right? So this one's relatively simple, and so is the next one. The next one is x squared is equal to 1. X to the 2nd power is equal to 1. And this one's going to yield 2 solutions because of the degree. And there's 2 ways of doing it. First way, you can take the square root of both sides. So you get x is equal to positive, negative, square root of 1 is just 1, right? Or you can bring the 1 over and then factor it out, which is how we're going to be dealing with most of the, the rest of these. So these two are the 2 most basic ones, right? Second roots of unity is positive, negative 1, and the first root of unity is just 1, right? Okay. What about the 3rd power? That's when it gets a little bit more convoluted than just doing random crap to it. So we want x to the 3rd power to be equal to 1. And we're not just going to take the cube roots on both sides, since notice how taking the principal cube root is only going to return 1 solution. We're looking for the other 2 solutions too, because this is a 3rd degree polynomial. So what we're going to do is we're going to move the 1 over and then factor it, because what you end up getting is that this is a difference of cubes. And factoring a difference of cubes, factoring x cubed minus 1, you get x minus 1 times x squared plus x plus 1, right? And now by the zero product property, this or that is equal to 0, right? So I'm going to split this into 2. Either x minus 1 is equal to 0, or the second factor, x squared plus x plus 1 is equal to 0. And this one, really simple to solve. Just add 1 on both sides. You get x is equal to 1, right? So this is your first solution that most people would typically guess, right? X cubed is equal to 1, of course. X can be equal to 1. So this is where the first solution comes from. But our second and third solution come from solving that right there. And notice how in the real world, we don't have any solutions. But we can work in the complex plane. So for this one, let's just complete the square. To complete the square for x squared plus x, you would want a 1/4. And this means you have to subtract 3/4 on both sides. So like this. And this means this left side is now a perfect square trinomial, which is x plus 1/2 squared, right? And then the right side remains the same. And then now if you want to take the positive negative square root on both sides, what you get is x plus 2 on the left side. On the right side, let's put down the positive negative first, right? Don't forget that. Square root of the negative 1 times the 3/4 is I. So we're going to put that down. Well, let's put that down here. Square root of 3, you can't do any much with that. It's just root 3. And the bottom, square root of 4 is 2, right? So this is the number we get after taking the positive negative square root of this. Final step is to move the 1/2 over by subtracting 1/2 on both sides. So what you end up getting is, and in fact, they both have a denominator of 2, so let's combine the fraction. You have a negative 1, right? And then you have the plus minus I root 3, and then all over 2. So these are your other solutions. These are the second and third, these are the second and third solutions to the third roots of unity, right? So I'm going to be writing down all of the solutions in a set rotation like this so that it looks nice. Let's put down 1 first, and then let's put down our complex solution. Negative 1 minus I root 3 over 2. And then you have negative 1 plus I root 3 over 2. Right? So these are the cube roots of unity. So at this point, it's still relatively simple, right? It's just a cubic equation, very easy to factor and to find the solution, right? Okay, let's move on to the fourth roots. And for this, this isn't actually going to be all that much more difficult. But yeah, let's get rid of our previous work and let's try to find the solutions to this. X to the fourth power is equal to 1. These are the fourth roots of unity. X is equal to the fourth roots of unity, right? So for this one, it's a polynomial. We need to do the same thing as we did for the other ones, and that is to move the 1 over. So we get x to the fourth, then subtract 1 on both sides, right? Like this. Okay, so this is difference of squares. This is just x squared squared, so we can rewrite this using the sum and difference pattern. We get x squared plus 1 times x squared minus 1. And you may notice that we can factor this further. However, I'm going to break this into 2 right now since these are both very nice to solve on their own. So we have the first factor, we have x squared plus 1 is equal to 0. And the second factor we have, x squared minus 1 is equal to 0. And I'm not going to factor this more since if you remember the second roots of unity, you can just move it over and take the positive negative square root. Same idea with this. So I'm going to solve this left-hand side first. We subtract 1 on both sides, you get x squared is equal to negative 1. And then take the positive negative square root on both sides, you get x is equal to positive negative, and then the square root of negative 1 is just I. So these are your first two solutions. And for this one, even easier, you just move the 1 over by adding 1 on both sides. And then you take the positive negative square root on both sides, and then the square root of 1 is just 1. So we get positive negative 1. So you have 4 solutions. 2 here, 2 here for this quartic, or the fourth roots of unity. And I'm going to write it down like this. X is equal to, let's start with the real solutions. We have negative 1, positive 1, and then our imaginary solutions are negative I, and then positive I. Yeah? There we go. That's the fourth roots of unity. And from here, it gets a bit more difficult. But yeah, let's give it a shot and see how it goes. Okay, so now we want to do x to the fifth power is equal to 1. Fifth roots of unity. And this is a little bit more difficult than you would expect, but let's get to work, right? So x to the fifth is equal to 1. Move the 1 over. X to the fifth minus 1 is equal to 0. And this is, well, let me give you a formula, okay? So I'm not going to use summation notation because this is a lot more simple than a lot of people make it out to be. A lot of math teachers make it out to be. However, note that x to the n minus 1 is always equal to x minus 1 times x to the n minus 1 plus x to the n minus 2 dot 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 all the way up to plus 1. Yeah, so you can see that this applies with difference of cubes. If you have x cubed minus 1, you get x minus 1 times x to the n minus 1, which is just 2, plus x to the n minus 2, which is just 1, and then all the way until plus 1. So you get x minus 1 times x to the second plus x to the first plus x plus 1, sorry. And same idea applies here, right? So instead of plugging in a 3 into n, now let's plug in a 5 into n, right? Because we're trying to factor the left side. First factor is this x plus 1 out here. Sorry, not x plus 1, x minus 1. And then on this right side, we have x to the n minus 1. N minus 1 is 4. And then x to the n minus 2, which is 3. And then x to the n minus 3, which is 2. And then eventually you get down to 1, right? So it's just addition. And don't forget that it is equal to 0. Okay, so zero product property. We know how to deal with this one. This one is kind of odd, right? But it's doable. Okay, so yeah. Now let's just split this up. X minus 1 is equal to 0. Or this big boy right here. X to the fourth plus x cubed plus x squared plus x plus 1 is equal to 0. Okay, here's where our real solution lives, since if you notice that if you just move the 1 to the other side, you get x is equal to 1 as our first solution. Right? Pretty simple. And then these are our remaining 4 solutions. There's 5 solutions, so 1, 2, 3, 4, 5, right? Because this is a quartic, we have 4 solutions that come from here. Notice that this is x to the 4th degree. You're adding all of these coefficients, and then the discriminant is, well, the quartic discriminant is negative. Well, no, not necessarily negative. That's not how quartic discriminants work. But just notice how this entire graph lays above the x-axis. So you only have imaginary solutions or complex solutions. Let's get started working on this. How the hell would you factor this? Well, we know that x is, you know what? Let's factor out an x squared from all of these, because we know that x squared is never equal to 0, and factoring out an x squared from like 1, it just gives you 1 over x squared. That means x cannot equal 0. But if you plug in 0 and check, it's not going to be equal to, it's not going to be true, right? So we're able to factor that out. So let's factor out an x squared. So here we have an x squared, and then on the inside you have, you're left with x squared plus x plus 1 plus 1 over x plus 1 over x squared. And now notice that there's kind of a nice symmetry, right? And we're going to take advantage of this, since notice that this term, and this term right here almost form a perfect square trinomial. Only difference is, well, the perfect square trinomial, by the way, would be x plus 1 over x all to the second power. Only difference is, if you expand it out mentally, this would be a 2 and not a 1. So let's just make it a 2, right? Why not? So we still have x squared, and then we have, well, let's group these 3 terms together, x squared, and then now we're going to make this plus 2, and we're going to subtract off 1 later. Plus 1 over x squared, right? And then we have our linears, and then don't forget that we still have to subtract off 1. Yep. Okay. Now this is a perfect square trinomial. Condense that, and then there's some cool things you can do later. So you get x plus 1 over x squared. This right here, if you group that, notice how you get this thing squared and then this thing to the first power. Right? Pretty interesting. And then minus 1. is equal to 0. Yeah? Okay, and of course, this is a quadratic now in terms of x plus 1 over x. So let's make a substitution. Let y equal to x plus 1 over x, so it's nicer to look at, right? So now all we need to do is factor the quadratic on the inside. And of course, there's alternate ways to do it, right? You can also just completely get rid of this x squared, since we can just divide everything by x squared, and it wouldn't matter since x is not equal to 0. And just find the roots of this equation, put it back in terms of x, and then find the roots of that. But I feel like this is a lot nicer, especially when it comes to the factoring aspect of it. I find it a lot more satisfying and conclusive, right? Because it doesn't look like you can't factor this. Obviously, you can factor it into two irreducible quadratics with integral, well, not necessarily integral, but with real coefficients. Anyways, to factor this, it might seem kind of difficult, but the way to do it, is to complete the square again, right? So, and notice how this does have real roots, right? This thing has real roots if y was our independent variable. However, it isn't, but for now, let's treat it as 1. So it does equal to 0. So this, therefore, when you complete the square, it's going to give you difference of squares, right? When you put it into, what is it called? Vertex form, it'll give you difference of squares, right? You have, well, let's just do that right now. You would add 1/4, right? But then that means to compensate it, you have to subtract off 1/4. And subtracting 1/4 from -1, you get -5/4. Right? Okay, so that's that. And here, this is now a perfect square trinomial. You can rewrite this as y plus 1/2 to the second power. And then, of course, you want to rewrite it as difference of squares, right? So you have something squared here, and then you also want something squared here. So instead of writing it as 5/4, let's write it as √5/2, but then square the entire thing, because they're still equal, but now it looks nicer because it's in difference of squares form. Don't forget, it's equal to 0. Finally, notice how difference of squares, you're actually able to combine these. So let's do that. So don't forget, you want y plus 1/2 minus this, and then y plus 1/2 plus that. So our first factor is y plus 1/2 minus √5/2. And our second factor is y plus 1/2. And then we did minus here, we're going to do plus √5/2. This one's kind of ugly, I'm going to rewrite it. Okay, that looks good. Finally, notice how we have two x's multiplied here, right? X times that, right? And there's two factors. So you can give 1x to each of these factors, and then it'll look nice again. So let me demonstrate that real quick. Rewrite the y in terms of x. Okay, that's step number 1. And then, so the y is x plus 1 over x. Oh, one more thing to note is that this number right here is actually pretty special, and so is that one. This one right here is just, you can rewrite it as the golden ratio. However, it's not going to be all that helpful to rewrite it as the golden ratio for our use case. However, I'm still going to do it. Notice that you can combine the fractions, so you get 1 minus √5 all over 2, and then multiply multiply in a double negative, right? So you have a negative. Well, let me just do it right here. You want minus, and this becomes a -1, and then a plus √5 over 2, right? Because if you distribute this negative sign into here and here, it becomes 1 minus √5 over 2, which is what you originally had. This right here, -1 plus √5 over 2, is 1 over 5. Phi is the golden ratio, so let's rewrite this as just 1 over 5. Yeah, maybe I'll dive into this in a second, but I want to finish off the algebra here. So I'll return to the phi thing later. And then here, also you want to replace the y with x plus 1 over x. And here, notice how the number is slightly different. You, instead of 1 minus root 5 over 2, you have 1 plus root 5 over 2. And this number is just normal phi, around 1.618, etc. Okay, finally multiply the x back in, and you see that you get 2 quadratics. Multiplying one of the x's into here, x times x gives you x squared. Negative 1 over phi times x gives you negative 1 over phi x. And then the positive 1 over x times our x that we distributed in is just normal 1. And same idea here, right? Multiply the other x into this. So we get x squared plus phi x, and then plus 1. Okay. And don't forget that they're all equal to 0. And notice now that we can do the zero product property. However, let's discuss this number right here first. Phi is equal to 1 plus root 5 over 2. Now, this is known as the golden ratio, right? And there's a multitude of reasons why. But I want to explain why this is 1 over phi and this is normal phi. So, let's just take the reciprocal of this, right? 1 over phi would be just the reciprocal of that, since you're flipping both sides. Think about it think of it as that. But, oh no, you have a irrational denominator. So let's multiply in a conjugate to solve that problem. The conjugate is just this sign, but flipped. So you get 1, but minus root 5 over 2. Oh, sorry, not 2. You get 1 minus root 5 instead of 1 plus root 5, and then you also have to multiply it into the bottom, right? Okay, and now this is just difference of squares. This becomes difference of squares when you multiply it out. Let's also multiply at the top. 2 times 1 is 2, and then 2 times negative root 5 is just negative 2 root 5, right? The bottom here, 1 times 1 is 1. And then you want to subtract off this last term squared, which is just 5. So here you get 2 minus 2 root 5 over 1 minus 5 is negative 4. Notice that if you divide both the top and the bottom by 2, basically multiply in a 1/2 onto both of the top and the bottom, the 2 become 1, this becomes just a normal root 5, and this becomes negative 2. Final thing, you can actually bring this negative outside, right? And then you can actually distribute that into the top. So this becomes a negative, and this becomes a positive. So this is 1 over phi. So notice here, phi is 1 plus root 5 over 2. Here, 1 over phi is what we put down here, right? So that's where this comes from. Anyways, our next step is now to use the zero product property on both of those. And I'm 100% certain that this is more difficult than any of the ones that we're going to do today. Anyway, and this, so this is equal to 0 or that is equal to 0. I'm going to do this down here so we have more space. But don't forget that we have one of our solutions already, right? We're just looking for the solutions of this. So this is equal to 0 or that is equal to 0. You get x squared minus 1 over phi x plus 1 is equal to 0. And in fact here, unfortunately, I don't want to keep this notation, even though it looks really pretty, because we're going to be completing the square. I'm not going to use the quadratic formula today, simply because I want completing the square. It's more difficult for some, but it's also a lot more satisfying to see the numbers play out without having to use some convoluted formula. That was more than just a sip of water. Anyways, yeah, let's keep going. So remember, this originally was 1 minus root 5 over 2. So we're going to write this as 1 minus root 5 over 2. Don't forget we have an x multiplied in and then a plus 1. And this is equal to 0, right? And then we have or, because this one can also be equal to 0. And same idea with this one. I'm also going to rewrite phi as the exact form. Okay, so now we want to complete the square for these. And it might seem kind of intimidating. However, let's just slowly work through it. Remember, to complete the square, what you're trying to do is you're trying to get a perfect square trinomial. And by altering the constant term. So what you want to complete the square is to first divide your b value, which is this middle coefficient, by 2. Well, sorry, no. Square the b value first and then divide by 4. I find that much easier to think about. Okay, and then add that on. You don't want a 1 here, right? You want this value there. And then you can have whatever number you want on the other side that's necessary to make it such that you have this in here. So take it slowly, step by step. B is that. So let's square this guy first. Okay. The top squared, let's just use, remember, a squared plus 2ab plus b squared, right? In this case, our a, well, in this case it's minus because it's a minus b. But anyways, our a squared is just 1 because 1 squared is 1. Minus 2 times that is just minus 2 root 5. And then our plus b squared, b is root 5. Square that, you just get normal 5. So you add 5, right? And then the bottom, 2 squared is just 4. Pretty simple. Here, 1 plus 5 is 6, sorry. And then minus 2 root 5 over 4. And then notice how you're able to divide both the top and the bottom by 2, right? Dividing 6 by 2, you get 3. Dividing 2 by 2, you get 1. But you still have the root 5 there. And then finally, dividing 4 by 2 gives you 2. So this is our b squared. Don't forget that we have to divide it by 4, right? So dividing this guy by 4, you just multiply it. It's just the same as multiplying in a 1 over 4. The 4 and the 2 multiply, you end up getting an 8, right? All right. So this is how to complete the square for the first one. And the second one, you can go through the exact same process. All I'm telling you is that there's just no negative sign there. Because if you think about it, only difference is instead of minus 2ab, right, which is what ended up giving us this minus root 5 term, you have a plus 2ab here instead because you have a positive sign. And that means instead of the negative version of this term, the root 5, you get a positive version of this term, the root 5, right? So completing the square for this left equation right here, you need to find some way to make this 3 minus root 5 over 8, right? And then on the right side here, you need to find some way to make this one 3 plus root 5 over 8. And to do this, let's just split up the 1. Notice that we have to cancel with the, well, okay. Let's just look at the 3 over 8 part for now. How do we get 1 from 3 over 8? We just have to add 5 over 8 to it, right? But notice here we have a negative root 5 over 8, sorry. And to be able to cancel with that, we need to add back root 5 over 8, yeah? So you add back a root 5 over 8. So think of it like this. Negative root 5 over 8 cancels with the positive root 5 over 8. And then the 5 over 8 adds with the 3 over 8 to make 1. All right, that's pretty simple. So, yeah. So you can kind of just replace the 1 with that. Right? And same idea over here. It's the same thing again, except, well, of course, you have to add 5 over 8, like 3 over 8 plus 5 over 8 gives you the 1. And then here, the root 5 over 8, you have to subtract off root 5 over 8 to cancel with the root 5, right? So this is equal to 1 and this is equal to 1. Okay, so almost done. Next step, let's just remember, this is the value that we want. We don't want this. So let's move this to the other side of the equation by subtracting it. So here we have x squared minus 1 minus root 5. Sorry, is this some negative or positive? I'm pretty sure it's a positive. Over 2x, right? But then here we want to add this value that completes the square and makes it a perfect square trinomial. And then remember, this would be adding here, but we want to move it to where the 0 is, so we subtract it on both sides. And then what you end up getting is a negative 5 plus root 5 over 8. And I'm going to write this a bit smaller since we have a similar situation going on over here, and it's going to take up around as much room. So 3 minus root 5 over 8. This is equal to negative 5 plus root 5 over 8. This side, same thing, right? We also want to move this to the other side. Now, that's going to give us negative 5 minus root 5. But remember, a negative on the outside means you can reverse the subtraction on the inside. So why don't we do that? Why don't we make this root 5 minus 5? Well, let's first write this down, and then I'll tell you why. So you get 1 plus root 5 over 2x. And then, remember, we broke this one up, so now we have this right here. Plus that, but we move it to the other side because we don't want it on our left side interfering with us. So we just get negative 5 minus root 5 over 8. Why don't we just multiply the negative in and just reverse the order of subtraction, right? Instead of 5 minus root 5, we can make this root 5 minus 5. Well, the point of completing the square, right, is to write this as a perfect square. And in this case, our perfect square would be x plus 1 minus root 5 over 4 squared, right? And we have to take the square root on both sides. Rewriting this as a perfect square, you get x plus 1 plus root 5 over 4 squared. Now, you can't reverse the order of subtraction because after you take the square root on both sides, well, first of all, notice that this is a negative number, meaning if you put the negative inside, it's still going to be, it's going to be root 5 minus 5 over 8, which is actually negative, because 5 is bigger than root 5, and you're subtracting it off. However, when you take the root, now you don't have an I to work with, right? And that makes it look like it's a real number. Like, it makes it look like this right here is a real number, which it isn't. You need to keep the negative on the outside to be able to recognize that there's an I that has to get put outside. Because this is currently negative, but it's not written in a way that would let us know that this is actually an imaginary number and not a real number. Because there's no I anywhere, right? Because this is negative, but it's hidden in there. So let's just keep it this way for now. Maybe I over-explained that a little, but regardless, let's work on this side again. Remember, the right side stays the same. All we did was rewrite the left side in an equivalent form. Right, and then over here, we also have the negative 5 minus root 5 over 8. Okay. And then, finally, take the positive negative square root on both sides for both of the equations. So on the left, you would end up with x plus 1 minus root 5 over 4. Right. On the right side, let's put on the positive negative first. This might look kind of intimidating, but I'll just tell you that the top, there's no better way to write it than just a nested root. So we have root of 5 plus root 5, since that's exactly what we're dealing with. And the bottom, root 8, if you can't do this in your head, this is root 4 times 2. Root 4 is just normal 2, so this is 2 times root 2, right? So the bottom becomes 2 root 2. One last thing, this negative sign becomes an I after you take the root. Alright, so that's this part done. Now let's move on to the right side. I just dropped it. Here, you would also take the positive negative square root on both sides, right? And then same exact thing happens, right? Notice that the mechanics are the same. Only difference is that instead of a positive, here we have a negative on the inside, but that doesn't affect anything at all. Since the 8 is the same, the negative is still on the outside. We're still taking a square root of it, so let's just read this as root 5 minus root 5. It's the same exact thing as the left-hand side right here. So positive, negative, root of 5 minus root 5 over 2 root 2i. One last step. Move this over. So we get x is equal to, and then of course this is going to be negative 1 minus root 5, and we can rewrite that as root 5 minus 1, right? Because actually currently this is a negative number right here. This is a negative number. Moving it over should make it positive, but writing it as negative 1 minus root 5, that looks kind of weird. So let's just reverse the order of subtraction and write it as what it really is. It's a positive number. It's this right here. And then of course we have the imaginary part too. Right? So this is the real part of these two solutions. This is the imaginary part of these two solutions. Okay. And then the right-hand side right here. Subtract that. This part is always positive before, so it's not like here where we have to make it look positive since it is positive. This one is just negative, so not much you can do about that. So you just get minus 1 plus root 5 over 4. And then write down the imaginary part of our answer, which is 5 minus root 5 over 2 root 2i. And yeah, so now count them, right? And we don't have any more equations to deal with. We have 1, 2, 3, right? Since you have a positive and a negative version. And then you have 4, 5, positive, negative version. So let's write down all of these in one line down here, right? Just to make it look nice and concise. So first solution, of course, is 1, because 1 to the 5th power is just 1, just like our original equation says. Now let's put it on this. Yeah, I'll just write it down normally. I don't know what else to do about it. You can try to combine the fractions, but I think that would just end up making it look a little bit messier. Maybe not. I'm not completely sure. But, well, no, not positive, negative either. I want to write out each answer distinctly. Okay, so that's these two. Now let's write down these two. We have root 5 minus 1 over 4. First, let's write down the minus. Root 5 plus root 5, root of 5 plus root 5. And then over 2 root 2i. Finally, our last solution is just the positive version of this, which is root 5 minus 1 over 4 plus root of 5 plus root 5 over 2 root 2i. Close bracket. This is our 5 solutions. Count them 1, 2, 3, 4, 5. Yeah, these are the 5th roots of unity. If you raise each of these to the 5th power, you get 1. The part most people get stuck on is trying to factor this quadratic right here. Well, not even just factor it, just find the solutions to it, right? Because you don't necessarily need to factor it fully before you find the solutions like we did. But yeah, these are the solutions, of course. All right, that's the 5th roots of unity. Let's move on to the 6th roots. Yeah, there's more. But the 6th roots aren't as difficult since 6 is an even number. There's some symmetry behind it. And by the way, all even roots will contain negative 1 and 1, and all roots the power of 4 will contain I, 1, negative I, and negative 1. And you'll see that when we do the 8th roots towards the end. Okay, let's do the 6th roots now. 6th roots are actually easier since well, 5 is prime, so you kind of have to factor it and do weird shit to it. 6 is not, so you're able to factor it in a variety of ways. So, let's do x to the 6th power is equal to 1. These are the 6th roots of unity. Don't take the 6th roots on both sides. You're going to lose 5 solutions if you do. Let's rewrite this by moving the 1 over. You get x to the 6th power minus 1 is equal to 0. All right. Factor this. Let me try that again. Factor this however you want to. You can do. Notice how this is both difference of cubes and difference of squares. Difference of squares, I'd argue, is easier. However, when you go down the difference of cubes path, you often get stuck. Because difference of squares, it gives you a sum of cubes times the difference of cubes, right? You get x cubed plus 1 times x cubed minus 1, and you're able to factor that further. However, if you do sum of cubes, difference of cubes, factor as if it's difference of cubes like this, right? Then you get stuck, because how the hell do you factor this? How do you factor that? There's no real solutions to this. Well, the solution is to complete the square. However, not by changing that. We fuck around with this middle term right here. So, well, first let's set this equal to 0, right? So x squared minus 1 is equal to 0, or this quartic, x to the 4th plus x squared plus 1 is equal to 0. So 2 of our solutions come from here, and 4 of them come from here. Here we do x squared is equal to 1, and then taking the positive negative square root on both sides, you get x is equal to positive negative 1. This is really simple. Okay, what about this? How do you factor this? Well, what you can do is, and this is generally whenever you have a quartic that's like x to the 4th plus something x squared plus 1. If the 1 is, well, how do I explain this? Let's just add x squared and then subtract it off again. And then we'll see what happens. Yeah, when you have a case that looks like this, where this last number right here is a perfect square, you just want to add the number that completes the square. However, you want to mess around with the middle term instead of the last term. So if you had this, then to complete the square, you want this to be a 2x squared. So let's add an x squared. Let's add an x squared to this, right? And then subtract it right away, right here. And by the way, this only works in this form. X to the 4th plus something x squared plus 1. And you can have the coefficients as long as this coefficient right here is a perfect square and this coefficient right here is a perfect square. Actually, it doesn't even, I'm not even sure if it needs to be a perfect square. As long, you can make this any number you want to. Just complete the square with this center coefficient. Now it's completed the square. Now we've done that. You can actually practice that on your own time if you want to. Regardless, let's keep moving. This is now a perfect square trinomial. So you might see where I'm going with this. This is x squared plus 1 squared, right? And then here you have a minus x squared. Reason. Oh, and the reason why we did this is because we have a difference of squares now, right? Anything in this form, just do this technique, right, where you complete the square by messing around the middle term. Because it's a perfect square, you end up with a difference of squares. Anyways, keep moving with this. Let's do x squared. First, you have to subtract x, right, and plus 1. And the second factor, you have to add it, because that's how factoring a difference of squares works. Okay, so now zero product property. These are two quadratics. So it's either x squared minus x plus 1 is equal to 0, or x squared plus x plus 1 is equal to 0. Okay, so this one right here, very nice. just complete the square. Same thing with that one. X squared minus x. To complete the square for that, you want this to be 1/4, and to make it 1/4, you have to subtract 3/4 on both sides. Right, and then here, same thing. Because the polarity of this middle term, as long as the coefficient is the same, whether it's plus or it's minus, it doesn't matter. The value to complete the square is still going to be the same. So here's 1/4, and of course to make 1/4, we have to subtract 3/4 on both sides once again. Okay, and here, rewriting this as a binomial squared, you get x minus 1/2 squared, and this gives you whatever. This is still the same, right? And then here, rewriting this as a binomial squared, you get x plus 1/2 squared. Right side stays the same. Yeah, okay. Take the positive negative square root on both sides. See, this is actually easier than x to the 5th, as I said earlier. So positive negative first, right? The square root of this negative gives you an I. The top, root 3 is just root 3. The bottom, root 4 is 2. Yeah. Same idea on this side. Sorry, no parentheses. X plus 1/2 is equal to positive negative I root 3 over 2. And we're almost done. Just move the 1/2 over on both sides. You get x is equal to, adding 1/2 on both sides, notice that you can combine the fractions. You get positive 1 plus or minus I root 3 all over 2. Right? Dude, I keep hitting the marker. There's a black dot on the table now. That's okay. For this one, same idea. Subtract 1/2, combine the fractions. You end up getting negative 1 plus or minus I root 3 over 2. Yeah, this is really good because we're done. You have 2 solutions here, 2 solutions here, 2 solutions here. 6 solutions total for the 6th roots of unity. So I'm going to write them all out now. And this is actually a lot shorter than the 5th roots of unity, so it's not going to take as much time. First, we have the positive and negative 1. Then we have, let's write down this one first. So we have a negative 1 minus I root 3 over 2. Then we have the positive conjugate version, so negative 1 plus I root 3 over 2. Then we have this one. Let's write 1 minus I root 3 over 2. And then 1 plus I root 3 over 2. These are the 6 roots of unity. Raise any of these to the 6th power. Is going to return you 1. Yeah. So that's it for this one. Alright. And let's move on to number 8, and then I'll come back to number 7. And I'll explain why that one is... Well, it's hard to find a good way to express the answers, even though it is absolutely possible. And by the way, you might, kind of have some kind of intuition as to why the 7th roots of unity might be difficult, maybe because it's another prime number, and a pretty bad one, right? 7 is never a nice number to work with when you're dealing with something like maybe factoring, right? It's prime, and it's also large, relatively large, and 5 is nice, but 7 isn't. So let's go to x to the 8th. Same idea here, as always. We're just going to factor this guy. In fact, I guess I could do x to the 12th, but it's the exact same idea as x to the 3rd and x to the 6th. You just factor it more. Anyways, let's do this first, and then I'll jump on to x to the 12th, right? Because the reason why I'm not doing x to the 9th... the reason why I'm not doing x to the 9th is simply because it's boring, right? The best way you can express the numbers with is just by taking principal cube roots, of course, of the third roots of unity, right? Which kind of makes sense since you taking the cube root because you want 3 times more solutions. So it's going to look something like that. And that's boring. So, Yeah, and same thing with the 12 roots, but just the pure number of it. Maybe I'll do it, and then I'll explain the 7th roots. Anyways, this one, move the 1 over so you can factor it. Yeah? My red pen is definitely running out. It was already running out in the beginning. I'm pretty sure you could have seen that. Factor is difference of squares. You get x to the 4th plus 1, and then x to the 4th minus 1. Right, equal to 0. Let's split it up, and then let's deal with this one first. So, this one's equal to 0, or the second factor is equal to 0. And I want to deal with this one first, this first factor first, because it looks kind of weird. But remember the strategy that we used to deal with, that we used last time of completing the square by adding a middle term. We can do that here too, because this is a quartic, and this right here is just a number. And if you just add an x squared term, you can complete the square and factor it more. So I'll explain how that works. Well, if you can't figure that out in your head quite yet, all we need to do here is add 2x squared to complete the square. However, we have to also subtract it off immediately to maintain equality, right? And then this is still equal to 0. And then here, this now is a perfect square trinomial, so we would rewrite it as x squared plus 1 squared. And of course, you want to rewrite this as a perfect square. So you need to take the square root of each of these factors. Square root of 2 is just root 2. And then square root of x squared is just normal x. And then squared. So this is now difference of squares. We can rewrite this as a quadratic. As 2 quadratics multiplied together. First, you want to subtract this. Right. So do minus root 2x first, plus 1. And then for the second one, you want to add it. So x squared plus root 2x plus 1, yeah? It's equal to 0. And let's break this up, yeah? Because 0 product property once again. And then now we have some goofy looking quadratics, right? Root 2, interesting. But this is equal to 0, and then you have an or condition, and then you have the second one is equal to 0. Same idea. Let's complete the square. How do you complete the square for this? Well, remember remember when we did 5th roots of unity, just first square it, then divide by 4, right? Squaring root 2 gets you just normal 2. Dividing that by 4 gets you 1/2. So you want to pull a 1/2 out of 1. And the way you do that is just by subtracting 1/2 on both sides. Leaves you with 1/2 left. And then remember you also subtract 1/2 on the other side, so you get a negative 1/2 on the other side. Same idea here. So you get x squared plus root 2x. Same number to complete the square since this is just the negative version, right? Plus 1/2. And then to get this 1/2, you had to subtract 1/2 on both sides. This is now a perfect square. So, yeah, you know what? Yeah, this is just a perfect square trinomial. So let's do x minus root 2 over 2 squared. And then the right side stays the same. Same idea over here, except now there's a plus, so you get an x plus root 2 over 2 squared. 0 to negative 1/2. Okay. Take the positive negative square root on both sides. On the left side, you get x minus root 2 over 2. And on the right side, you get, okay, well, positive negative first. The I can come later. Square root of 1 is just 1. And then root 2 on the bottom. And you have the I. Typically, high school math teachers would ask you to rationalize the denominator. Of course, we're not. Well, I mean, you know what? To make it look nice, let's do that. Multiply root 2 on both the top and the bottom. 1 times root 2 gives you root 2. Root 2 times root 2, which is what's going on the bottom, gives you a normal 2. So you get root 2 over 2. Yeah? Same thing happens over here. And of course, this is the exact same number that you're taking the positive negative square root of. So on the right side, you're also going to get positive negative root 2 over 2i. Almost done. You just add root 2 over 2 on both sides now. And then that gives you your final answer of x is equal to root 2 over 2 plus or minus root 2 over 2i. And you can see why I wanted to complete, well, no, not complete the square, rationalize the denominator from this step, right? Because you have a root 2 over 2 and a root 2 over 2 here. And if you were to do the complex analysis for this, it has a very nice geometric reasoning. And if I go on a quick short side tangent here, it's because, well, if you do root 2 over 2 plus root 2 over 2i, it's this coordinate right here. This coordinate right here is, well, this number right here, if this were the imaginary axis and this were the real axis, this number right here would just be root 2 over 2 plus root 2 over 2i, right? Since you're going up in the I direction, root 2 over 2, and the same, and then going root 2 over 2 in the real direction. This is 45 degrees, right? So that means this, and that should be the same. 45 degrees is it makes it symmetrical across, yeah. Anyways, quick short side tangent over. And this side, same exact idea. Yeah. Wait, sorry, no, not that. I was thinking towards the end, we can actually combine the fractions, right? This only looks nice because it's the same number. One is real, one is imaginary. But, I mean, at the end of the day, to make it look better, just combine the fraction, right? But this works better for you if you're working, like, with the unit circle on the complex plane in complex analysis. But, anyways, this one, negative root 2 over 2 plus or minus root 2 over 2i, yeah? So we have 1, 2, 3, 4 solutions. Where's the other 4? This is the 8th degree. We forgot about that, no? Okay. This should be relatively simple if you recognize this. This is actually the 4th roots of unity, but let's go over it again because I want to do all the algebra. So this implies, if you factor this real quick, you get x squared plus 1 times x squared minus 1 on the left-hand side, right-hand side. Still equal to 0. And then each of these is now equal to 0, so you get x squared plus 1 is equal to 0, or x squared minus 1 is equal to 0. And then finally, x squared is equal to negative 1. Just move the 1 over, right? Here, you add 1 on both sides. You get x squared is equal to positive 1. And then, one last step, take the positive negative square root on both sides. You have the positive negative, right? And then the square root of negative 1 is just I. Here on this side, positive negative square root of 1. Well, you have the positive negative, and the root 1 is just 1. So you have 5, 6, 7, 8 solutions. 1, 2, 3, 4, 5, 6, 7, 8. Right? Alright, so we're done with x to the 8th power. And I'm going to do x to the 12th power because it's funny. Yeah, for now, let's write down all of these. And I'm going to be combining the fraction for these guys too. Right, okay. So as a final answer, let's write down these 4 first because they look nice. You have negative I, negative 1, and then 1. So you have 2 real solutions, and then 2 purely imaginary solutions, and then you have 2 that are mixed, and 2 that are complex. This one, yeah, let's start with this one actually. So we have negative root 2 minus I root 2, all over 2, right? So that's what it would look like if you combine the fractions. And then don't forget the conjugate. Well, kind of the conjugate, I guess, the complex conjugate, because these are both irrational. You can look at it both ways. But if you took the complex conjugate, it would be that. On the left-hand side, same idea. Root 2 minus I root 2 over 2. And then finally, root 2 plus I root 2 over 2. So you have 1, 2, 3, 4, 5, 6, 7, 8 solutions. 8th roots of unity. Each of these, when raised to the 8th power, gives you 1. And feel free to actually check my answers, right? Because raise this to the 8th power, it's going to be 1. Raise that to the 8th power, it's going to be 1. Right? That's the 8th roots of unity. And we're almost done, because we just have one more left. That is the 12th roots of unity. And then I have to go over the 7th roots of unity, which is actually going to take a lot of time. But for now, let's just do the 12th roots of unity. Yeah? Okay, for this one, you know what, let's just wing it. Anything can happen. Okay, so the 12th roots of unity. X to the 12th power is equal to 1. It looks intimidating. 12 solutions, but they should all be relatively familiar, I think. Right? If I just... Let me check that real quick, actually. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah. These are all... They all look... The numbers are going to be familiar. Okay. Yeah. For this one, let's factor x to the 12th minus 1. Looks intimidating, high degree, but just remember, let's factor this as a difference of squares first. So what you end up getting is x to the 6th plus 1, and then x to the 6th minus 1. And I'm not going to break it up quite yet. Let's just factor this all the way down to the fucking ground. X to the 6th plus 1. Let's use the complete the square method using the middle term instead. And just add a 2x cubed plus 1, right? Notice how... Sorry, no, I'm actually doing all of this in red. X to the 6th stays the same. But now you're adding a 2x cubed. Notice how this completes the square. Right? And then you have to immediately subtract off a 2x cubed to compensate. And then let's keep the right side the same. The other factor the same. Alright. And then for this one, you need to... this is a perfect square trinomial. So, what is this? X cubed plus 1 squared. And then you have to subtract off... Sorry, I don't... Actually, no, this wouldn't work, because you can't express this as a perfect square. My apologies. How else could you do this, then? Well, x to the 6th plus 1. It is also sum of cubes, right? So, writing this, you get x plus 1. Well, sorry, not x plus 1, x squared plus 1, right? Since the cube root of x to the 6th is x squared. And then x to the 4th plus x squared. Sorry, no, not plus, minus, because this is sum of squares now. Plus 1, right? And then on the right side, this is just, well, treat it as a difference of squares. Yeah? Yeah, okay. And then what you get on the right-hand side here is x cubed plus 1, and then x cubed minus 1. This is equal to 0. Alright, break it up more. This is sum of cubes, difference of cubes. This is, well, yeah, this is basically a reduced, but I'll show you how you can break this down even more into linear terms. This one, we can use that good old factoring method of completing the square using the middle term. Alright, for this one, I want to show you a cool way to do this. And the first step is just to turn this into a negative, right? So this is just x squared minus negative 1. And now this is a difference of squares, since negative 1 is just I squared. So I'm going to rewrite this negative 1 as I squared, and then we'll factor that as our next step. Anyways, we have a lot more to go. So here, we would want to add x to the fourth. To complete the square for this, we want to make a difference of squares, right? So you can't subtract x squared here and then add x squared, because that would make a sum of squares. You want difference of squares. So you want to make this plus 2x squared. And the way you do that is by adding 3x squared, right? Negative 1x squared plus 3x squared gives you plus 2x squared. And that means you have to subtract off 3x squared immediately afterwards. So we'll do that right here. Okay, and then sum of squares, sum of cubes there. X plus 1 times x squared minus x plus 1. And then difference of cubes here. So you get x plus 1, difference of cubes is x minus 1, x squared plus x plus 1. And Jesus Christ, this is equal to 0. So, this is linear, it's quadratic. These are basically irreducible, but they're the same quadratics as we faced before. This is also relatively simple, right? Because this is now difference of squares. So let's rewrite this as x plus I, x minus I, right? This middle guy right here, this is now a perfect square trinomial. This is x squared plus 1 all squared. And then you also want to rewrite this as difference of squares to be able to factor it. So this 3x squared needs to become a root 3x all squared. Alright, and almost done. I'm going to just write down the rest of these guys. It shouldn't take too long. But damn, it is taking a long time. And the cool thing about working with a power with as many multiples as this is, you can factor this however the hell you wanna. Treat this as difference of difference of cubes, difference of squares, difference of fourth powers, difference of sixth powers if you want to. If you know it'll all work. And then you can do factor by grouping if you like to. If you do if you factor this into x squared minus 1 times a bunch of other crap, or even just factor out an x minus 1 and then do x to the 11th plus x to the 10th plus x. There's so many pathways you can get to find the solutions of this. This is just like the one where we keep the powers kind of distributed evenly, but there's so many creative ways you can do that. And I find it pretty fun, but you know what? Keep this concise. We'll do it like this. Yeah. And finally, I'm just going to rewrite this and break everything up. So we have x plus I times x minus I, right? This middle one right here, we just have this be x squared, and then this is the difference of cubes, so, sorry, not cubes, squares, so subtract this first. Right, and then the plus 1 from here. And then our second factor is x squared, and then now we have to add root 3x. And then our plus 1 from here, right? And then we have the rest of these factors right here. We have x plus 1, x squared minus x plus 1, x minus 1, x squared plus x plus 1 equal to 0. Now, these are all of either the first degree or the second degree, right? Let's break it up finally. Let's do with these first degree ones first. So we get either x plus I is equal to 0, or x minus I is equal to 0, right? Or, next one right here, x plus 1 is equal to 0, or, and then our last linear term right here, x minus 1 is equal to 0. And then this would give us x is equal to negative I. This would give us x is equal to I, just isolate x. And then this would give us x is equal to negative 1. And then this would give us x is equal to 1. We solve the quadratics, right? So, or this, well, you know what? Let's do the easier ones first, right? This and that. X squared minus x plus 1 is equal to 0. Or x squared, and then the positive version plus x plus 1 is equal to 0. Or. And then we have those two left, right? However, let's solve each of these individually first. This one, complete the square, right? Rewrite it. At this point, I'm pretty sure we've done this one twice. This one's done once in x to the 6th power. Should I do it again? Well, sure. For the sake of completeness, I'll do it. For this one, I'm gonna write this in red since this is still just one enormous equation so far. Complete the square, x squared minus x plus 1/4. This means subtracting 3/4 on both sides. Same idea right here. X squared plus x plus 1/4 means subtracting 3/4 on both sides. And then, of course, rewriting this as a perfect square trinomial. This is a perfect square trinomial. Rewriting it as a binomial squared, you get x minus 1/2 squared. And then this is still equal to -3/4. This one, rewriting it as a binomial squared, you get x plus 1/2 squared is equal to -3/4, right? Take the positive negative square root on both sides, and then move the 1/2 over. I'll just write it. X is equal to this. You have a positive 1, right? And taking the square root of this side, you get positive -I√3/2. However, this is both over 2, so I'm going to write it like that. Same idea on this side, right? So I'm not going to explain it again, but we get x is equal to, this side is -1, however, plus or minus I√3, and then all over 2. So that's the two solutions that come from these quadratics. So far we have 1, 2, 3, 4, 5, 6, 7, 8 solutions. We need 4 more, and that comes from these two quadratics, which we have not written down yet. Okay, so let's work on those then. Or x squared minus √3x plus 1 is equal to 0, right? And of course, I'm gonna write the other one down here, but I want to work through this one first, because notice that, these two are basically identical to each other, just the real part is negative. But that's only because the center term, right, is just the opposite, is just negative. So same thing's going to apply to here, right? The other solution, we're going to have a negative real version of, the real part is just going to be the negative of the real part of this, and then the imaginary part is actually going to be exactly the same. Well, it isn't, but because we have the positive negative, it takes care of it. Okay, so to solve this, complete the square. Completing the square, square that, and then divide by 4. You get 3/4. So you want to pull out a 3/4 somehow. And to do that, you just, and to pull out a 3/4, you just want to subtract 1/4 on both sides. So this is still √3. And then plus 3/4, right? Then you subtracted 1/4 from both sides to get this 3/4. Rewriting this as a binomial squared, you get x minus √3/2 squared. And the right-hand side is still the same. Now we want to take the square root on both sides. Positive negative square root, of course, don't forget. So on the left-hand side, we're left with whatever's on the inside there. On the right-hand side, positive negative square root of this is, the I goes on the outside. And then on the inside here, you have 1, and then, 1/2. Okay, I don't know why I'm overcomplicating this. I thought this would be something where we had to rationalize it. No, it's not. Anyways, we don't have any repeat solutions, by the way. And we know this because, do we have repeat solutions actually? No, we don't. We should not, at least. Okay, we don't because, I'll just write down all the solutions and I'll show you the nice part towards the end. But you might be seeing it coming already because we're basically done at this point. Anyways, just add root 3 over 2 on both sides. And then you get root 3, right? And then plus or minus, I'm just going to write this as I over 2. And then, right, okay. And then the positive version, as we discussed earlier, the real part is just negative, right? As we've seen and that's like been the case for this one, right? Since the b is just negative. I already discussed this, so. Or, that, but except b is negative. So we have a plus root 3x plus 1 is equal to 0. And then I'm just going to write this really, really concisely. X is equal to negative root 3 plus or minus I over 2. Ooh. And in fact, it's possible to do the 24th roots too, now that I think about it, if you look at it on a unit circle. But there's so many solutions at that point. But I mean, it's still completely rational. It's expressible in terms of roots. That's really cool. But 12 solutions is enough for today. So this, that. The solutions of these quadratics are pretty cool. Because notice that up here, root 3 is the imaginary part. But down here, root 3 is actually the real part. And then the 1's the imaginary part down here. But then originally we had the 1 as the real part. Pretty interesting, right? And if only I could go over the complex analysis, this would make a lot of sense, right? If you saw me draw that unit circle earlier with the spokes poking out, that's kind of how you would interpret all of these results. Anyways, 12 distinct solutions. Let's write them all down. And then we'll go over x to the 7th power is equal to 1. Okay, I'm going to take another seat because it's going to take me a while. Let's put down these. X is equal to negative I, positive I, negative 1, 1. So that's 1/3 of the solutions. Let's just write them down. Yeah, this first, that second, and then this one, and then that one, Yeah, okay, so negative 1 minus I root 3 over 2. Negative 1. No, sorry, not negative 1 and then negative 1 plus I root 3 over 2. Then next up you have positive 1 minus I root 3 over 2. And then positive 1 plus I root 3 over 2. Alright, down here we have negative 3. Oh, Jesus Christ. We have 4 more solutions. That just hit me. Negative root 3 minus I over 2. Negative root 3 plus I over 2. This negative is in the fraction, by the way. And then finally, we have the positive root 3 minus I over 2. Then positive root 3 plus I over 2. These are the 12th roots of unity. I'm going to box it. I'm struggling here. Jesus. It's not even a good box. Close enough. Okay, and you have 12 solutions. I'm going to count them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Really nice, don't you think? Okay, and that's it for the 12th roots of unity. Back to the 7th roots and why it's kind of difficult. And I mean, well, like, the numbers that we skipped are, of course, 7, 9, 10, 11, and I have an explanation as to why we skipped each of them. 11, the explanations are going to be very similar to 7, right? You can work it out yourself. It's because it's prime, right? And I'll show you what we do with 7, and you kind of just got to believe me that if you were to try it out, 11 is going to go around the same way for you. And then 9, as I discussed earlier, it's just the cube roots. It's just the cube roots applied to our third roots of unity, right? Because it's 3 times more solutions, I guess. 10 is just, well, 10 might look cool. However, 10 is 5 times 2. And if you remember the 5th roots of unity, they were pretty bad. So doing the 10th roots of unity, doing the 10th roots of unity is kind of like doing the 6th roots of unity for the third. Like, if you remember the 6th ones, they look basically the same as the third roots of unity, right? Kind of like how the 10th roots of unity look the same as the 5th, right? I mean, similar structure, but they're going to be around the same. At least, that's my guess. Maybe not. Prove me wrong for the 10th one. I haven't actually went over those before, but that's why I skipped each of those. And I'm going to demonstrate why we skipped the 7. Yeah. Okay, and that's it for the 12th roots. I need to check that everything is still recording, of course. Alright. My whiteboard's getting dirty from all this writing. Alright, 7th roots of unity. And I'll explain why it isn't... Well, it is doable, but it's ugly. Now, I'll explain why. Feel free to look into it yourself. I'm going to factor it down until it's a linear and then 3 quadratics for you guys. This one, same idea as all the other ones. Subtract 1 on both sides. You get x to the 7th minus 1 is equal to 0. For the left-hand side, notice that this is just, you can factor out an x minus 1, as I discussed before. And then all you're left with is x to the 6th plus x to the 5th plus x to the 4th plus x cubed plus x squared plus x plus 1. God damn. It's pretty bad. Imagine doing partial fractions with this. Anyways, you now know that... Well, yeah, let's just break it up now. X minus 1 is equal to 0. Right? Which implies that x is equal to 1, right? That's one of our solutions, of course. I'm going to just box that for now, since that's the one solution. 1 appears in every single nth root of unity, where n is a positive integer, because that's how you define it. Anyways, this one... looks nice and neat since it's just descending. However, notice that there's 7 terms. And that is precisely the reason why it is so awkward. It's the fact that there are 7 terms in this polynomial right here. You can't do factor by grouping. Since there's 7, it's a prime number of terms. You can't split it, you can't group it, right? So remember what we did for the 5th though? Why don't we try that? The 5th roots of unity, where we just factor out an x squared. In this case, we have to factor out an x cubed to get the same kind of symmetry. And it actually does look kind of promising at first. So here, let's factor out an x cubed from all of this. And what you get is x cubed plus x squared plus x plus 1 plus 1 over x plus 1 over x squared plus 1 over x cubed. Kill me already. Oh my god. Oh, what the hell? Okay, so let's now complete the cube, right? You have the cubic terms. Let's complete the cube. I'm going crazy. So to complete the cube, I'll just remind you of the coefficients. It's 1, x cubed, 3x plus 3 over x, and then plus 1 over x cubed. Binomial theorem, anyone? Yeah? So, same idea as before. Let's add on 2x to make 3x. Right. And then, now let's make this 3 over x and plus 1 over x cubed. Right. Okay, so we completed the cube. We'll work on the compensation later. What about completing the square? We still have this untouched. This is untouched, and this is also untouched. So we can complete the square in the same way. Just add 1 and then subtract 1 later when we do the compensation. So the x squared stays the same. However, the 1, now we have to make it a 2. plus 2, right? And then, of course, the 1 over x squared stays. All right, now let's do the compensation for these. We added 2x, and then we added 2 over x. So we have to subtract 2x and then subtract 2 over x immediately afterwards. We're right here, one more thing to compensate for. This change term, we made it a 1 to a 2, and to do that, we added 1. That means we have to subtract 1 immediately afterwards to make it stay the same. Close the parentheses. And x cubed stays. We write all of these, right? Here, we can write this as a perfect cube. We write this as a binomial cubed. This is a binomial squared. This is... You can factor out a -2, and then that guy is just a constant. It's very nice looking. It just stays there. X plus 1 over x cubed plus x plus 1 over x squared minus 2 times x plus 1 over x, and then minus 1. Right? They're nice, right? Like, it's a cubic in terms of x plus 1 over x. Just find the solutions to the cubic, and then you're able to factor it. You're able to factor it. I'm going to stop you there. Right? Let's make the substitution first, and let's see what happens. Let y equal to x plus 1 over x. Alright, here we just have x cubed again. This is just y cubed plus y squared minus 2y minus 1. And here comes the reason why this is so fucking bad. And doesn't equal 0. yeah. It's because you can't factor that. That's very, very difficult to factor. Right? Like, remember previously, we took the quadratic, because it was a quadratic. All quadratics are factorable into linear terms. If it has real roots, right? But this is a cubic, and a cubic is like 10 times more difficult to deal with, especially, because there's like 10 times more configurations it could possibly have, and we don't have any one very nice way to solve it unless you use the full, not Cardano's, but the full cubic formula, the general cubic formula. And that's going to give you the roots. And unfortunately, applying that, there's no really nice way to express the roots of this cubic. That's my last gulp of water for today, for this video. So, what I'm going to do, because of this unfortunate event, is I'm just going to write, let alpha be equal, alpha, beta, and gamma be roots of p of x, where p of x is equal to x cubed, this polynomial right here, plus x squared minus 2x minus 1. Right? This 2, if it wasn't a 2, if it was a 1, we'd be able to factor by grouping, and that would be really, really, really nice. However, you can look it up on Wolfram Alpha. This doesn't really have any nice way of expressing it in its exact form. But we know it's factorable. We know that these are all real numbers, because if you just graph it or you find the discriminant, there's 3 real solutions to this bad boy right here. There's 3 real solutions. So you can technically factor this. And your coefficients would all still be real. You wouldn't be dealing with weird imaginary coefficients. And that's what makes it such that this method right here is valid. You still have a polynomial with real coefficients. So, let's just factor that now. You get y minus alpha, y minus beta, and y minus gamma. Yeah. is equal to 0. Y minus alpha, y minus beta, y minus gamma. And yeah, this, if you've done high school math so far, think of this as intercept form, right? You can always just factor, you've always been able to factor a polynomial into its, with 3 real roots into, well, with any amount of real roots into intercept form, where the real roots are just subtracted from your array variable. If the leading coefficient was 1, then the leading coefficient here is also going to be 1, meaning this is a valid factorization, right? It's just really unfortunate you can't express it with better numbers. Yeah, so, anyways, for this, now let's rewrite this all in terms of x, right? Since there's 3 factors now, and there's 3 x's here being multiplied together. So why don't we do that? Y is x plus 1 over x minus alpha, and then I'm going to do the same thing with the rest of these terms. Right? And then just distribute 1x into each of these, right? And then you get 3 quadratics out. So you have this solution, and then you have the solution to 3 quadratics. So x times x is x squared. And then minus, well, I'm going to write this in red. And then you have minus alpha, and then alpha times x is just alpha x. And then x times 1 over x is just 1. Here, same idea. And, of course, same idea with the last term as well. Sorry, not last term, the last factor. Okay. You can look up what the value of alpha, beta, and gamma are equal in their exact form, and then you can complete the square for each of these quadratics, and then you find the 6 solutions that come from this. But I'm going to leave that up as an exercise to the viewer, since the exact form of these 3 numbers, the roots of p of x, where p of x is that, they're pretty horrendous, right? But I mean, of course, I'm willing to bet that there's going to be symmetries involved, of course, but too much work, and it takes a lot of space to do as well. So this is your one, well, I'd call it a trivial solution, right? And then the rest of your 6 solutions for the 7th roots of unity come from these, but they're all really, really ugly, which is why I chose to skip this one initially. Yeah, that's it. Really cool, right? You can find the 24th roots of unity. If you think factoring is satisfying, which I personally do, I would try to find the 24th roots of unity, 18th roots of unity, something like that, because I feel like that just sounds really fun.